In this problem, we're going to be finding probabilities for a normal distribution, and then also we're going to look and see if we can apply the central limit theorem to find a probability for the sampling distribution of the mean. And there's a couple things to note about this problem. One thing is that when you hit new version, you will sometimes see a less than symbol here, and it'll be talking about a probability of a value falling less than a certain boundary. And sometimes it'll be a greater than symbol, and that will be talking about the probability of a value falling greater than a certain value. So you may have to do a lot of versions before you hit one. Sometimes I get several in a row that are less than, sometimes I get several in a row that are greater than, and sometimes it just goes back and forth. So there's really no way of predicting which one you're going to get. So you'll want to know how to answer both types. And there's not a huge difference, but you do need to know how to do the less than one. And if you know how to do this one, it's really easy to do the one with the greater than symbol. So we'll start with this version, and then we'll do one with the greater symbol after. So it starts out by telling us we have a population of values that's normally distributed, and the population mean mu is given as 56.2. I'm going to go ahead and put that into my spreadsheet that I've prepared already. The population standard deviation sigma is given as 7.3. They do tell us that we're going to be selecting samples of size n equals 12, so we'll go ahead and put that here. But that is not really going to matter until we get to the second part of the question. For the first part of the question, it says find the probability that a single randomly selected value, in other words, one single x value, find the probability that x is less than 50.3. So the x value that we are interested in is 50.3. That'll be the boundary, and we want to know what's the probability that this x is going to be less than that. So now let's take the mean and standard deviation and set up the scale so we can understand in terms of how many standard deviations from the mean these values are. So we're just going to put in the scale. So we know if it was a standard normal distribution with a mean of 0 and a standard deviation of 1, then we would have z-scores across the horizontal axis just representing a number of standard deviations away from the mean in each direction. But with a non-standard normal distribution, it's still helpful to understand what the actual x values are, how they align with standard in terms of standard deviations from the mean. So we can set up the scale by using the mean here, and I'm going to use an absolute reference to the mean cell. And then I'm going to add the standard deviation and also use an absolute reference on that as well, putting in the dollar signs. Putting in the dollar sign as well here. Then we're going to multiply that times the z-score in that cell here above. And so this gives me the x value that corresponds to 3 standard deviations below the mean. And because of the way I just programmed that, I can actually copy this over and it'll go ahead and do all of them for me. Oops, that's not what I meant to copy. I meant to copy, let me move this over a little bit. I was trying to copy the formula in this cell here. I don't know, I've never seen this happen where it's copying my ink. I didn't even know that was possible. Let's try this again. Really strange. Okay, good. All right, so I got that now. So those are all my x scale values. All right, so now I want to put in the x scale value 50.3. This is the boundary we were told to use. So I'm going to go ahead and put that in here, 50.3, right around here-ish. All right, so I'm expecting this answer to be kind of close to 0.5 since we know the total area under the curve is 1, and this is somewhat close to the mean. 50.3, it's a little bit less than the mean, and since we're looking for less than that value, we're looking for the area to the left, and so that's less than half of the total area under the curve. So this answer is going to be less than 0.5, but kind of close to 0.5. Now we can use the norm distribution in Excel. So we're going to find the left area by doing norm.dist on the x value 50.3. For some reason it didn't go do what I wanted. Try that again. What's going on here? Try it one more time. There it goes. Okay, had some spaces in front of my equal sign that I didn't realize were there, and then as soon as I moved those, it was working again. All right, and then I can put in my mean and my standard deviation. Oh, and I forgot to say true for cumulative, as always. All right, so there's my left area, 0.2098482. It says to round to 4 decimal places. So that's the answer for the first part, but I'll just round it and put that in. Oh, the wrong one. There we go. So here's 4 decimal places. The value to the right here tells me to round up, so I'm going to round that last digit 4 to 5. Okay, so that's the first part. Now, the second part says find the probability that a sample size of n equals 12 is randomly selected with a mean less than 50.3. So now I'm interested in whether or not the central limit theorem would apply, and that applies if you either have a population that was normal to start with, or if you have a sample size greater than 30. Here we do not have a sample size greater than 30, but we do see that the original population has a normal distribution, which means that the sample mean will also be normally distributed. So I can use the central limit theorem here. And what that means is that we're just going to do everything the same, except instead of using sigma for the standard deviation for the mean, we're going to take that standard deviation and just adjust it by dividing by the square root of the sample size n, and then we have a new standard deviation just for the distribution of sample means. So we have a special name for this. We call it the standard error, or SE for short. And so now that I'm working on the second part of this question, I'm going to need a scale that's a little different because now my standard deviation is different. So I'm just going to get rid of this for a moment. And now I'm going to make a new scale for my Xbar values. So for my sample mean values. So before I was using this standard deviation to add on to the mean. Now I'm going to be using a different standard deviation. So I'm going to be using the standard error, but I'm still going to start with the same mean. And I'm going to add to it, instead of adding the standard deviation, I'm going to add the standard error. Being careful to do absolute references again. And then how many times am I going to add or subtract the standard error? Well, that's based on the z-score. So that I'm going to leave as a relative reference so I can copy this easily. And then I'm going to go ahead and stretch that over. So I've got all my values scaled out there, and I think I'll just format these to be 1 decimal place. It's a little easier to look at. And so this is my X-bar scale, all the sample means. Some black ink there again. And when we have a smaller standard error, smaller standard deviation, the curve tends to be squished in and more tall and narrow because there's less space in between the values, technically. Which doesn't really affect how you answer the question, but it just helps to understand why, even though we're using the same X-score boundary, which was 50.3, we're still going to use 50.3 as we did before, but now it's going to be relatively different. So 50.3 is all the way back here, which is so far away from the mean. Remember last time it was like right in this area, I believe. So now it's way farther, almost, almost 3 standard deviations out. So we're going to see a much different answer in the probability since the area to the left of this value is going to be much smaller than what we saw before. So now, instead of using this standard deviation in my norm dot distribution function, I'm using the standard error instead. That's really the only change, and then I get my answer. And notice how much different that is. That's a much, much smaller answer. Okay, and then we'll go to 4 decimal places. So 4 decimal places here, here. And so the number to the right is 5, which tells us to round up. So I'm going to do it like this. Okay, now that's how you would answer both parts of that. Now, what if it was a greater than symbol? Okay, the only difference is that instead of giving this as your final answer, you're going to subtract from 1 to get the area on the opposite side. So we'll go through this again, and since I already have all this set up with my scales, I think we can get this done really quickly. All right, so I'm going to just change the values for this version of the question. So now I have a mean of 225.5. Then I have a standard deviation of 3.6. The n is 15. And the x boundary is 224.5. And then now I'm going to look at my x scale right here and see that the value 224.5 on the x scale is relatively pretty close to the mean. So we should see an answer that's a little bit greater than 0.5, since now we're interested in the area to the right because it's a greater than symbol here now. And so we'll still get the left area using norm.dist. For part A, we are going to go ahead and use the standard deviation, and that gives us the left area, but the right area, which is what we want for this question, is just 1 minus that. Okay. And so we see the answer there. And as I was predicting, it's greater than 0.5, a little bit greater than 0.5. And I'm trying to copy it and paste it, but having some trouble. So I'll try one more time. Okay, and then down to 4 decimal places. Okay, now for part B, I'm going to be using the scale. Get rid of this because now it's going to be a little different because I have to use a different scale. Use my Xbar scale, and the boundary 224.5 is now relatively 224.5 is back here. So as you can see, it's a good deal less or farther away from the mean in terms of standard deviations. And so now we're going to have a larger answer greater than 0.6, so significantly greater. I'm going to see a much different answer. So now the only thing I have to do though is to change in my norm.dist from using the standard deviation in the third argument to using instead the standard error. Okay, so that's what I want instead. And now I have the answer, as you can see, a much higher probability of getting a mean in that range than getting a single individual random value in that range.